Hey everyone. In this lecture, we're going to talk about conservation of mechanical energy. Um, I think that, well, I guess we'll see, but I'm hoping I can hit sort of everything that we need uh, for this topic, conceptually at least, uh, in around an hour. And if I can, I think what I'll do for the next lecture is just make it sort of a problem-solving session where you can see me work through some more examples to get comfortable with these ideas. We will see how it goes, though. Okay, so the first thing I want to do here is just review what we've kind of covered as far as work and energy goes so far. So let me just take this from my other document here. Um, these are the different forms of energy we have, right? We have kinetic energy, which we're going to write as a big K. We have gravitational potential energy, which is mgy, and then we have elastic potential energy. I think I want to rewrite this maybe like so, just so that we can think of this as being, or all these different formulas as being sort of what we would use when we're talking about, say, a one-dimensional problem. Even though we'll often be dealing with two-dimensional problems, and you might be wondering why I wrote this script y here instead of just a normal y, and the reason I decided to do that was because um, we won't always be able to uh, sensibly set our y equals 0 for the gravitational potential energy to be the same as y equals 0 for the elastic potential energy. So to kind of indicate that, I've just written this as a script y here instead of a regular y, and remember that these two symbols are not the same, right? Uh, I don't think that we'll actually have to worry about that in any of the examples that we're doing in this lecture, but I just wanted to make it clear. So let me say that one more time. Um, when we're working with gravitational potential energy, we can set our y equals 0 to be anywhere we want, and this is because only changes in gravitational potential energy are meaningful, right? As we discussed previously. However, the equilibrium position of a spring, right, assuming it's fixed uh, in some position, is always going to be just, well, it's going to be uniquely defined, right? We don't have the freedom to say the equilibrium position of a spring is wherever we want it to be, and that's the big reason for this notational difference here. Anyway, let's also remember what we discussed about work, or how we defined work, and the work energy theorem. So let's say work and the work energy theorem. And what we had for those two things was this set of equations, right? And I just want to also remind you that this is a definition, or a way of calculating work that only really is going to work when we have a constant force. And I've also been maybe a little fast and loose with differentiating between uh, this being a displacement vector, or um, well, it is a vector, right? But in the way that I've referred to it, maybe I've been interchangeably calling it a displacement or a distance, and I don't think that that's been an issue so far, because all of the um, examples we've considered have been forces being exerted over a straight line, and I don't think we'll really work with any examples that don't follow that sort of template. But it is important to remember that a displacement and a distance aren't always the same, right? Okay. So these are our equations, right? And just remember this last one here, since I didn't really say anything about it It's just that the change in kinetic energy of an object is equal to the net work done on the object. Okay, so let's talk about conservation of energy in the absence of non-conservative forces. And so in equation form, we can simply write something like this. We can write that the initial mechanical energy of a system or of an object is equal to the final mechanical energy, right? And if we wanted to see like what this might look like, I want to stress that this is not how this will always appear, right? But it could look something like this maybe. And I'll talk about why it won't always necessarily appear like this in just a second here. I want to write this differently though. I want to write script y. Okay, so the reason it won't always necessarily look like this is because we might have problems where, for instance, there are no springs involved, right? In which case we wouldn't need to write this term here and this term here. Or alternatively, if we think about maybe motion in the x direction, or a problem that involves motion in the x direction, there won't be any change in gravitational potential energy, right? So we can kind of do away with these terms here, this one and this one. But most generally, it will look like this. And if you want to think of an example where this would be a perfectly suitable way of writing conservation of energy, would be maybe like fixing a spring to the surface of a table or something, and so it's vertically oriented, right? And then putting like a marble on top and then compressing the spring and then seeing what happens. And that would involve all three forms of mechanical energy that we've discussed so far, right? Kinetic, gravitational potential, and elastic potential. But we won't always need all three of these terms here, as you'll see in some of the examples we do. Okay, so let's talk about what this means a little bit. And I want to just write out that all we're saying here is that if we compute, say, E naught numerically, right, then compute E numerically, we would obtain the same numbers. But in general, we probably realize that the initial velocity won't necessarily be equal to the final velocity, right? Or speed, I should say. And the initial y position of the object won't, in general be equal to the final y position of the object. And the, initial compression or extension of the spring won't necessarily be equal to the final compression or extension of the spring, right? And so what we have is we just have that while the total energy is remaining constant, the kinetic energy might, say, increase while the gravitational potential energy decreases, right? And it's not really so much that we worry about any one of the particular values of like the kinetic energy or the gravitational potential energy or the elastic potential energy, but we want to ensure that, well, I shouldn't say we want to ensure. What we find is that their sum stays the same in the absence of non-conservative forces, right? So let me think about this. So actually what I want to do is probably right here is maybe just draw your attention to what this might look like. One way you could represent this, right? And this is often done with like bar graphs. And so let me just say pictorially, there we go. We might, and I'll have to probably take this all the way down. We might have something like this, right? So let's say that in green here we have some arbitrary object, right? It doesn't really matter what the specifics are, because we can still get the point across without getting too specific here. But we might initially have some sort of object that has like a lot of kinetic energy and no gravitational potential energy. Or let's just say that this U denotes the sum of the gravitational potential energy and the elastic potential energy, right? So what we would find though is that like maybe then for some reason the kinetic energy of the object decreases, but we find then that the potential energy has to correspondingly increase. And I made this so that when you add, the height of one of these columns to the other column, right? So if I add, say, like K1 and U1, the height should be the same for all three of these arbitrary cases that I've come up with, right? And so here it's like the kinetic energy is decreasing even more, and the gravitational potential energy, the potential energy is increasing, right? And I drew this so that, here, this column plus this column has the same height as this column, right? And this is maybe I should have written just E here because this is just our total energy. And adding K1 and U1 up sort of pictorially here would result in one column that's the same height as this one, and then the same goes for this here too. I don't know if this helps, but I know this is a common way that this is represented in textbooks, so I wanted to use it. Okay, let's look at an example now though. And this is an example where we'll kind of see, I think, very clearly how this works, because what we're going to do is we're going to compute the total mechanical energy of a projectile that's being launched up, or that has been launched up, straight from the ground, right? So with only a y component of initial velocity. And we already know what's going to happen here from kinematics, right? And so this would just be a good way to confirm that, everything we've been saying about energy is true, because it should correspond exactly to what we would get using kinematics. Anyway, let's get into this. The first thing I want to say is this is a result from kinematics that we're going to need. I'm going to say, recall from kinematics that the maximum height of a projectile that only has a y component of initial velocity. There we go. Jeez, I'm sorry, it's late and I'm tired. Is given by this. It's going to be okay. Wow, I need to get it together. Okay. It's this, okay? It's the initial speed squared over double the gravitational acceleration. And this is a result we're going to need here. So with that out of the way, though, let's start calculating some of these things. And so for the first part here, right, I'm going to say when the projectile is at the level of the ground, it has no gravitational, I'm just going to start calling this GPE, actually, gravitational potential energy, right? And so we could write this. We could write that the initial mechanical energy of the projectile is just its initial kinetic energy, which is 1/2 m v naught squared. Okay? That's all we can really do as of now. But we'll see that this result here for part A is important for what's to come. Okay. So when the projectile is at half its maximum height, what we have that y is h over 2, and if h is v naught squared over 2g, then h over 2 is v naught squared over 4g, right? So let's just write that out. And so we'll calculate the mechanical energy here, and I'm going to write this now as E1. So we have 1/2 m v1 squared, right? This is now the kinetic energy when it's at half of its maximum height. and there's going to be some gravitational potential energy now because it's no longer at the level of the ground, right? And we actually know exactly what its height is at this time. It's going to be what we found here. So let's fill this in. Oh, and I also am going to need this result from kinematics, and you can show this, right? Actually, the way you would show both of these things is from this equation, in case you were curious. This is how you would find that, and this is how you would also find what I'm about to say, which is that at half the maximum height, the speed is going to be v naught over the square root of 2. And then we have to remember to square all of this. And what did we say? We said that y1 is just... I'm going to have to probably use a couple lines here anyway, so I'll just write that out. So it's m. So y1 is big H over 2, right? So then let's clean this up a little bit. We're going to have, well, what this works out to be is 1/4 m v naught squared, right? And then mg, and we already found big H over 2 to be v naught squared over 4g. 4g, right? And so when we go through and cancel the g's, what we find is 1/4 m v naught squared plus 1/4 m v naught squared. And lo and behold, right, this actually works out to be 1/2 m v naught squared, which, right, was our initial kinetic energy, which was our initial mechanical energy, right? So far so good, right? We're getting a result here that's consistent, which is good. And remember that this result, right, what it's saying is just that the energy is conserved. That's what we're trying to show here, while also getting some practice with actually calculating these things. Okay, so the last thing we want to do was calculate the mechanical energy when it's at its maximum height, right? So when the projectile is at its maximum height, remember that the velocity, well, I should say the y component of velocity goes to 0 at maximum height, but this is just a one-dimensional problem, so we'll just write v2 equals 0. Thus, E2, right, the mechanical energy at the projectile's maximum height is just going to be mg big H. And remember that we found big H to just be v naught squared over 2g, right? And this is 1/2 m v naught squared. So that's good, right? Because this is again, this is equal to E1, which is equal to E naught. And so we see that so far, at least for this, you know, sort of simple one-dimensional problem where we're sort of just kind of, you know, confirming some things that we already knew from kinematics, or I shouldn't say we're confirming them, but we're using things that we already knew from kinematics to confirm that so far this idea of conservation of energy seems consistent. But we do see that it is consistent, right? So that's a great sign, I think. Very exciting, right? Cool. Okay, I just want to stress this. And I want to say in the previous example, right, the one we just did, what we have is we have that the kinetic energy, and I'm going to write this as a function. Whoa, oh, that's right. I accidentally hit Alt-Shift, so my Russian keyboard is taking over. Okay, here we go. So the kinetic energy is a function of time, even though, so one of the nice things about working with energy is you'll notice that in our general equation here, right, there's no explicit time dependence. And that's one of the nice things about it, is we don't have to often worry about the time. But we know, right, that in for example, this problem that we just did, that obviously there is time dependence. It's just not appearing in the way we're working through the problem. But so what I want to say is something like this, is that this kinetic energy as a function of time is, well, it can be written like that, right? Where now we're just making the dependence on the velocity, or the time dependence of the velocity, explicit. I forgot what I was saying, but anyway, so this is decreasing, right? And it's decreasing as U, as our gravitational potential energy, which is, remember, this increases. But at any time during the projectile's, let's say it's ascent, right, because we're only considering it going from ground level to its maximum height, but this is going to be true sort of even if we considered the other half of the motion here, where it descends, right? But we find that the total energy is just the kinetic energy plus the gravitational potential energy, and this is a constant, right? Just to stress this, because this is a very important idea, and I want to make sure. Well, I want to make sure that no child's left behind, right? Okay, so that's good. Let's look at another example here. In this example, we're going to think about dropping a bowling ball, all right, which has a mass of 3 kilograms from a height of h equals 1.5 meters above a spring's equilibrium position onto the spring, which is fixed vertically to the ground. And before the bowling ball hits the top of the spring, right? Maybe we can imagine there's a little platform on top of the spring. But before it hits the platform, the spring is at rest in its equilibrium position. Okay, so there's no elastic potential energy associated with it initially. Anyway, if the spring constant is K equals 500 newtons per meter, what is the maximum compression of the spring? So let's look at this. I want to make a sketch, first of all, of what's sort of happening here in case it wasn't completely clear. And we could, represent it like this, maybe. Let me make this a little smaller. I don't think it needs to be that big. There we go. Cool. So this is kind of what's happening. Okay. I don't know why it's not giving me a space on the other side, but that's fine. So, let's see here. Okay, initially, and I don't think I explicitly said this in the problem statement, but we are imagining that the bowling ball is being dropped such that its initial velocity is 0, right? So initially, the bowling ball has only gravitational potential energy. So our initial mechanical energy, right, is just going to be mgh. Not too bad. And then notice here, right, so what I've done here is I have decided on where I want my y equals 0 to be for purposes of calculating gravitational potential energy. And this is an example of where we can make, as you'll see, the equilibrium position of the spring line up with our y equals 0. So this is a fairly nice example. And this dotted line here, right, this is what I'm calling my y equals 0. Okay. So then, okay, so what you might be tempted to do here is calculate the kinetic energy of the bowling ball right before it hits the platform, right? And that is fine. There's no reason you can't do that, but we don't have to do that because we're not losing energy anywhere in this system, right? Because we have no mention of air resistance or friction or anything like that, right? And so we can assume, I think, pretty safely that energy is conserved. So what I'm going to do is I'm just going to look at, let's say, looking at when the bowling ball instantaneously comes to rest and the spring is maximally compressed, we find. And so this might also be a little bit unclear, so let me just talk about what's happening here. So we're imagining, right, we drop this bowling ball on top or onto a platform that's fixed to a spring. And if we could make an animation of what's happening here, it would look something like, well, we drop the bowling ball, it hits the platform, the spring maximally compresses, right? It goes down delta Y. And when the spring is maximally compressed, the kinetic energy of the bowling ball instantaneously goes to zero, right? Because what would happen in real life here is this would compress a certain amount and then it would shoot back up, right? And so the bowling ball is initially falling down, and then after the spring has reached its maximal compression, it's going to launch the bowling ball back up. But there is some time at which the kinetic energy is zero, right? Because the bowling ball is changing, its velocity is changing directions, and we know that it has to go to zero at some point for that to happen, right? So that's the time that we're thinking about here. And so what we could say is that, and I'm going to call this E2 because if you wanted to do the kinetic energy thing, maybe you would call that E1. And that might be a good thing for you to try for yourself for some practice here. But let's look at E2, and what we're going to have is there's going to be some elastic potential energy associated with the compression of the spring, right? And we're going to have a negative gravitational potential energy because notice now, right, that in this position, the platform and the bowling ball are below our y equals 0. And there's no reason, we talked about this in the last lecture, but there's no reason we can't have a negative gravitational potential energy. And this again comes back to this idea that I'm just going to keep blathering about incessantly, that only changes in gravitational potential energy are meaningful, not specific values. So what we find here, right, when we equate the initial mechanical energy and the final mechanical energy is this. I have mgh equals, and I'm just going to copy and paste this, like that, right? And we'll write this out one more time because I want to arrange it so that we sort of see what's happening here. And what's happening is that we get an equation that is quadratic in delta y, right? And so this would be another instance of us having to use a solver or the quadratic formula to figure out what delta y is. Okay, so let me just use my fancy calculator here to do this. This is one of the things I actually don't have in my notes. I don't know why, but we can solve it pretty quickly with the power of Mathematica, right? So I'm going to do this on my other monitor. Okay. about I just show you what I'm getting here? Let me make sure I got all the numbers. Okay, I think I'm good. So what I'm finding is, obviously this is just Mathematica doing the quadratic formula for us, is these two equations, right? And notice that we do wind up with 2. And so that's a little peculiar, you might be thinking. Let's evaluate this numerically, though. See what happens. So the gravitational acceleration is 9.81 meters per second squared, right? The mass should be 3 kilograms. We said the height was 1.5 meters, and the spring constant was 500 newtons per meter. I think that looks good. And so numerically, we find two different results here. And you might be wondering, well, which one do we choose? And I am going to say that the way that I have solved this problem is such that delta y is positive, right? And I accounted for the fact that we're at this position, we're below our equilibrium position by just putting a minus sign out here. But notice that I could have equivalently written this like this perhaps, and it's mathematically the same thing, right? And so this is just another instance where I'm kind of using my understanding of what's going to happen, right? Because I think we all kind of have an idea of what this looks like in real life, to rig my equations so that I solve for a positive quantity. But you could have, said delta y is negative and written a plus sign here too. Anyway, the point of all this is that one of these solutions, right, and I just use delta instead of delta y, but one of these solutions here gives us a positive number and the other gives us a negative. And I would suggest that because our assumption, right, because of the way we wrote our equations, is that the positive solution here is the one to choose, because it corresponds to our decision to think of delta y as being a positive number in and of itself, right? So you should find that it's approximately, let's say, 0.48 meters of compression of the spring. Cool. Okay, let's move on then. Now we want to talk about what conservation of energy looks like in the presence of non-conservative forces that are doing work in the system. So I'm just going to put a bunch of words down, and what I want to say is that conceptually we know that we can calculate the total mechanical energy of a system via summing the kinetic, gravitational, potential, and elastic potential energies, right? And clearly, we also know that we can calculate it being the energy at some later time, right? Assuming we have all the information about the system that we need. And then also, I want you to recall, right, that we identified the dimensions of work to be the same as those of energy. And I'm just going to assert this, right? So I am asserting then, and I want to type this up as well, very carefully and clearly. So just bear with me while I put a few more words down here. If we calculate the mechanical energy let me say, E naught of a dynamic system, and dynamic here just means that things are changing, right? Don't worry so much about that word. If is weird to you. At some time, t equals t naught. Then again, at some later time, t equals t naught plus delta t to obtain E, right, the mechanical energy at that later time. The difference between the two quantities, E naught and E, is determined by the work done by non-conservative forces in the system. So in equation form, we can write this. That delta E, right, is simply the work done by the non-conservative forces. And I want to, let's see here, I want to center this, and then I want to put a box around all of this because this is pretty important. And notice, right, that the expression that we had for conservation of mechanical energy in a system where we had no non-conservative forces doing work actually falls out of this equation, right? Because in that case, we have delta E equals 0, right? Because if there are no non-conservative forces doing work, obviously this term here is 0, and that just states what we had for conservation of energy earlier, right, where we were thinking about there being no non-conservative forces doing work. So this is a pretty important and powerful result. And again, I want to stress that you don't worry so much about the time thing here because, you know, we will often not have to think about time when we're talking about conservation of energy. And that's one of the advantages, right? That's one of the things that's nice about this framework for solving problems is that we don't have to worry about time. Because remember back to kinematics, right? Sometimes, you know, we would have a problem where we didn't, you know, or we weren't asked to solve for the time, but we needed it, you know, we needed to solve for it at some point along the way to get what we really cared about. And the nice thing about energy is most of the time we can just not worry about the time dependence. As long as we realize that, you know, it's there implicitly, but we don't actually have to work with it. And hopefully this becomes clear as we do some more examples. So let's look at some examples of conservation of energy in systems where we have non-conservative forces doing work. Okay, so the first example I want to consider is this one where you push a block of mass m equals 50 kilograms, let me say initially at rest on a smooth frictionless patch of floor such that it has an initial velocity of v naught equals 8 meters per second just as it begins to pass over a patch of floor where the coefficient of kinetic friction is mu sub k equals 0.6. How far does the block slide before it comes to rest? So you can imagine maybe something like, I don't know, the boundary between two rooms in your apartment or house maybe, right? Where say like in one room you have a hardwood floor that's pretty smooth and, you know, maybe you can neglect friction, and in the other room maybe you have like carpet, right? And the friction is going to be more noticeable in that room. And so it's like the point is that as soon as the box is on the frictiony surface, it has this initial speed. Okay, hopefully that's okay. So let's do this kind of like maybe what I would call the naive way, right? To see how we can approach these problems involving non-conservative forces doing work. And so we might start out by saying, okay, let's write out the initial mechanical energy. And this is all taking place on a flat ground, right, where we don't have any changes in gravitational potential energy. So we can just say, well, my initial mechanical energy is all kinetic, right? And you might be thinking, well, hey, my floor is probably a couple meters above, let's say, like, the street outside or something like that. And there are two reasons that doesn't matter. The first is that we can always define our y equals 0 to be where we want it, right? And the second is that even if we wanted our y equals 0 to be, say, at the street level outside, what we would find is that we have the same term for the gravitational potential energy being added to all of our equations, right? And there's no mathematical reason we can't just get rid of that and still have the mathematical truth of our equation or equations preserved, right? So if you don't believe me, just try it and you'll see that it can just go away, and it doesn't matter that it was there in the first place, right? Okay, so anyway, this is what we have for the initial mechanical energy. It's all kinetic, and it's just 1/2 mv naught squared, right? So let's think about the final mechanical energy, right? The final mechanical energy, well, we're now thinking about when the box has come to rest, right? So I'm going to say, looking at the final mechanical energy, it's just 0, right? Because there is no longer any kinetic energy, and we agreed not to, well, maybe we didn't agree, but I'm not including it, to include the gravitational potential energy, right, for a good reason. And so this is what we have. And so we have, like, well, this situation where we initially have some energy and later we have no energy. And so something's going on, right? And what's going on is the friction force is taking energy out of our system, if we want to think of it that way, right? So we're at this point now, and we're like, hey, well, E naught doesn't equal E. So, we suspect something's going on, okay? And so I'm going to say, okay, so something must be taking energy out of the system. And it has to be the work done by friction, right? And thinking back to what we, said about friction, right? This shouldn't be a surprise to anybody. This is given by, and we'll say Fk. This equals the coefficient times the normal force, right? And this is simply mu k mg, right? So this is the magnitude of our friction force, and the corresponding work it does then is, and it's going to be this. I'm going to call it W sub f, and it's going to be mu sub k mg script L, right? So this is what we want to solve for, this distance the block slides. And then if we want to do it this way, we can write cosine of 180 degrees, right? Because say the box is moving to the right, well, the friction force then is pointing to the left because it always opposes the motion or intended motion of an object. And this, I personally would never write it this way because I just have gotten very comfortable with the idea of just putting the sign in as the SIGN, right? As is appropriate. And so what this works out to be is just this. All right, negative mu k mgl. So we can write it kind of like this, our conservation of energy expression. Let me see how I wrote it in my notes first. Yeah, just the way I was planning on writing it. Is like this. Actually, no, this is not the way I plan on writing it. Let's write it the way that we had our expression for conservation of energy in the case of non-conservative forces doing work. And remember, it was just this, right? The change in energy, change in mechanical energy is given by the work done by non-conservative forces. So I'm going to fill this in, and remember delta E is just E final minus E initial. And so this is 0 minus 1/2 m v naught squared. And on the right-hand side here, we just determined that the work done by the non-conservative force, there's only one in this case, is negative mu k mgl, right? And so we can do some things here. We can cancel the m's, right, because they're common to both sides. So we could just think of dividing both sides by m, and the masses go away. So it turns out that I didn't actually even need to give you the mass here, which is kind of interesting, I think. And upon doing so, right, we find that this becomes v naught squared over 2 equals mu k gl. And the final step here is just divide both sides by mu kg, right? And so we find that L is given by v naught squared divided by 2 mu kg. And I actually did calculate a number for this. So we'll just put that in because I did it. And I found it to be about 5.44 meters. Which is, what, I don't know, about 18 feet or something. So maybe you have a really big house or apartment, but not super unrealistic, I guess. Okay, so that's cool. And hopefully going about this in sort of the naive way, as I would refer to it, helped, because, you know, it's like, the idea is you try to apply conservation of energy and it doesn't work. So then you start thinking, okay, well then there has to be some non-conservative force, there could be more than one, right, doing work in this situation. And then you work to determine the nature of the work done by the non-conservative force, and then everything is fine, right? Okay, just one more example here, and then I think the next video I do will just be like a problem-solving session where I work some more examples for you, and hopefully by the time that's done, you're fairly comfortable with these ideas that we've been discussing, and you know, are able to do the homework. Well, practically speaking, hopefully you actually are learning things and understanding this, right? That's arguably more important, but okay. Anyway, so in this example, you launch a projectile from ground level with initial velocity of 10 meters per second. Now you know how to calculate the maximum height it reaches from kinematics, but you measure that it falls short of that height by a value of delta y equals 1.5 meters. So what we want to do is figure out what the work done by the drag force was during the projectile's ascent. Okay. Now I'm going to just do a quick sidebar here and talk about the drag force, because it's something I'm technically supposed to talk about. I don't think it's super important personally, but that's what the learning outcomes say, so let's try to respect those a little bit. So what I want to say about the drag force is the drag force is given by, and let's write it like this. I'm going to write it just as c v squared, okay? Now, c is some constant, and there are other constants that go into c, right? And you can find these. I wrote out what they were in the homework problem if you want to see what that all involves. But the important thing about the drag force, right, is that it's given by some constant times the speed squared, okay? And this is problematic because Well, you know what? Let's do this. Let's just think about what's happening to an object in free fall, right? If we're considering the drag force, and then you can see, I think, pretty clearly when after we've done that, what the issue is with this this drag force. So let's say then for an object in free fall, experiencing a drag force, Newton's second law gives something like this, right? And I'm going to use this dot notation that we have seen before. But we have now, right, that the drag force, say for an object that's falling down towards the surface of the Earth, is going to point upward, right? So this is a force that points upward. And then we still have the gravitational force, right? The object's weight that, you know, pulls it down. And then we set this equal to the mass times the acceleration. And this is all happening in the y direction, right? We're just talking about a one-dimensional example here. So if I rewrite this using the dot notation, I'm going to write this. Remember to put a dot over this. Okay, and then we have minus mg, and then this equals m, and then remember the acceleration, right? So velocity in the y direction is just given by y dot, the first derivative of position. This is the second derivative of position, okay? Now, this makes it clear, I think, that we have a differential equation on our hands, right? And we could write this one more time, maybe. So just putting this sort of in the standard form of a differential equation, right? And it's okay if this is very unfamiliar, because the whole point of this is that we're not really going to do much when it comes to solving problems involving drag forces because of the mathematical difficulties, right? But this is a differential equation, and it's not even linear because we have a derivative being squared here, right? And this is tricky mathematically, and that's why in this problem, right, if you didn't understand this, it's okay, but the whole point is that in this problem we don't want to try to solve for the drag force or the work done by the drag force like directly, right? And we'll see how we get around that. So I'll just say we don't want to deal with this, right? We don't want to deal with this. So let's use our idea of conservation of energy instead. Okay, so then this is similar to before, right? The initial mechanical energy of the projectile is all kinetic, right? Note that we're implicitly here choosing our y equals 0 to be at the ground level, right? The starting height of the projectile, and is given by, this was pretty much the same thing we had before, so this shouldn't be terribly surprising. And we're going to write E naught equals 1/2 m v naught squared, okay? Now we know in the absence of air resistance or drag, right, same thing. Drag is essentially like friction, really, when it comes down to it. It's like a friction force that something moving through a fluid, right, air is a fluid, experiences. And so in the absence of air resistance or drag, we know that the final mechanical energy is just going to be mgh, or I should say big H, because that's what we typically use for the maximum height, right? However, in this case, the actual final mechanical energy is mg, and then it's big H minus delta y, right? Because we somehow know that this object doesn't go quite as high as it would if we had no air resistance, right? Don't ask me how we know, we just know. And so what we can do here then is we can write, remember delta E is just the work done by the non-conservative forces, so we start with this and then we just fill it in. And delta E is E final minus E initial, right? So that's just going to be what I call E prime minus E initial equals the work done, and I'll make this explicit. I'll say that this is the work done by the drag force. And then we fill this in, right? So we have mg big H minus delta Y minus 1/2 m v initial squared, right? And this equals the work done by the drag force. And that's it, right? Actually, so we can't, I guess we can't actually calculate this if we don't know the maximum height. So maybe you can, well, no, I shouldn't say that. I was going to say you can make up a number, but if the number you make up isn't actually realistic, then you might wind up with a positive number for the work done by the drag force, right? And that is not okay, because as the projectile moves up, right, the drag force, in the sense that it's very much like friction, opposes that motion. So the drag force for a projectile that's ascending points downward, right? And so there has to be a certain realism to your choice of the maximum height of this projectile. Well, actually, no. You know what? I'm sorry. I'm insane. Because we know what we know what this is, right? Remember that we found, okay, I'm losing my mind. Remember that we found earlier that the maximum height was v0 squared over 2g. I don't know why that didn't occur to me, but so that, let's do that. Let's finish this up and substitute that in, right? So, like I said, I'm tired. I apologize. I actually, like, okay, this is going to make me sound like a complete dingus, but I started recording this lecture earlier in the day, and I got, like, most of the way through it, and then realized that OBS wasn't recording for some reason. And that kind of reminds me of this story about Isaac Newton when he was a professor at Cambridge, maybe? You know, some college in the UK, or university, I should say. And it was, like, apparently a university holiday, and he showed up for a class that he was teaching and just gave a full lecture apparently to an empty room. So I don't know, maybe absent-mindedness and physics go hand in hand. Anyway, this we found, right, to be v0 squared over 2g, and then minus delta y minus 1/2 m v0 squared. And this is the work done by the drag force. Okay. So, because apparently I'm not in the best mental state right now, I'm going to just make Mathematica do the algebra for me really quickly here, and you can see what this looks like. So, I'm going to call v0 just v, so Mathematica doesn't get mad at me, and delta y just delta. It's just the symbols, it doesn't really matter too much, right? And I'm going to have this solve for, well, I guess all I'm really going to have it do is simplify the left-hand side here, because we already have it solved for the work done by the drag force, right? Which it will do very nicely. And we find the work done by the drag force is just negative mg delta y in this case. And this is indeed negative, right, because the mass is positive. Our convention for g is that it is the number positive 9.81. meters per second squared, right? And this was also positive, as I stated it in the problem statement, right? 1.5 meters. It turns out that what we actually need here is the mass. But remember that that is always going to be positive, right? And so we would find that the work done by the drag force is indeed negative in this case, and that's reassuring because we just discussed why, right? Because the drag force points down when the projectile is ascending, and so the displacement, right, points up, and the drag force points down, and so we know that the drag force, its magnitude is changing because we saw that it depends on the speed squared, right? But that doesn't mean we can't be confident that it does negative work. And so that's that. Okay, that's it for this lecture. I will be putting one out tomorrow. It's Sunday. I think you can probably see that on my screen. Well, it's Monday actually, I guess technically. So I'll be putting one out later today, another video. And as I said, in that one, I just intend to maybe talk about a few more minor conceptual things, but mostly solve problems. And I think what I will do is just take some textbook problems and go through and do them with a tablet. Okay, I will see you next time.